In this video, we are going to walk through two examples using the different series comparison tests that we've seen in class. So here's example one. Let's determine the convergence or divergence of the series, the sum, as n goes from 1 to infinity, 1 over n times the square root, quantity n to the fourth plus 1. Now let's walk through the steps that we're going to take each and every time we use one of these series tests. The first step in our series test is that we want to find a different series. We need something to compare to. So we want a different series, hopefully a simpler series, that has the same rate of growth as the given series. So to figure out what series that is, we're going to go back and use these ideas of n behavior models and rates of growth to throw away the unimportant terms, so to speak, when we start talking about n values that are getting very large. So here what I mean is if I take the limit as n goes to infinity of the function 1 over n times the square root of n to the fourth plus 1, the 1 that's appearing here underneath that square root is not really contributing to the rate of growth of this function at all, so we can throw it away. We can say that in the limit of the function that we're given is the same as the limit of the function 1 over n times the square root of n to the fourth. When we do the algebra and we simplify that, we see that that's the limit as n goes to infinity of 1 over n cubed. And 1 over n cubed is a much nicer function than the function we were originally given. So what our conclusion is that we would expect the series that we're given to have the same behaviors, by behavior I mean convergence or divergence, as the series, the sum goes from n from 1 to infinity of 1 over n cubed. Now that we have something to compare to, let's move on to step 2. Now that we have this easier, simpler series, what we want to do is determine the behavior, either the convergence or the divergence, of the new series. So we have an idea of what should hopefully be in store for us. Now our much nicer series is this series, the sum goes from 1 to infinity, 1 over n cubed. This is what we would call a p-series, where the p-value, which is the power, is 3. Now 3 is an integer that's bigger than 1, and we've studied p-series before, and we conclude that the series that we're comparing to, sum n is 1 to infinity of 1 over n cubed, converges by using the p-series test on this easy series. Now that we have some intuition about this second series that we've introduced that we somehow want to compare to, what we need to do is use a comparison test to really formalize our intuition that the two series have the same behavior. And this is where we get into two options that we've discussed before in great detail. We have the direct comparison test, which I abbreviate by DCT. We also have the limit comparison test, which I'll later abbreviate as LCT. If we want to use the direct comparison test, since we know that the series, the sum as n goes from 1 to infinity of 1 over n cubed, since we know that's a convergent series, we need to show that the terms we're adding up in our given series are actually smaller than the terms that we would be adding up in this new introduced series. That is, we've shown that we have this other series that has a finite value, and we need to show that what we have is something that has a smaller value, from which we'll be able to conclude that what we're looking at has a finite value. On the contrary, if we want to use the limit comparison test, we don't really need to argue anything about what's bigger or smaller, but what we do need to do is take a look at this somewhat nasty looking limit as n goes to infinity, of the ratio of the terms of our series. So up in the numerator of this complicated fraction, we have the terms of the series we were given, and in the denominator, we have the terms of the series that we introduced ourselves. We need to take a look at the limit as n goes to infinity of that quantity, and we need to first of all figure out that the limit exists and that it has a value that's going to be strictly in between 0 and infinity. Now for this example, we're actually going to walk through both series tests. Both series tests apply here, and we want to just get practice using them. So let's first start with the direct comparison test. Now in order to use the direct comparison test, we're going to start with something that we feel like is hopefully clear, which is that n to the fourth plus 1 is going to be a number that's bigger than n to the fourth. And that's something we feel really comfortable with. And we eventually want to work from this inequality to an inequality involving the things that we want, which is 1 over n square root of n to the 4th plus 1 and 1 over n cubed. The first step in going from what we have to what we want is to take the square root of both sides. And because we're dealing with numbers n that are larger than 1, we know that we can do this, and this inequality is going to be preserved. So the square root of n to the 4th plus 1 is larger than the square root of n to the 4th. The next step is to take this new inequality and multiply on both sides by n. Again, since n is positive, we don't have to worry about the inequality flipping on us. The inequality is preserved, and we conclude that n times the square root of n to the 4th plus 1 is larger than n times the square root of n to the 4th. Last, note that when we have an inequality like this and we reciprocate it, and take 1 over, we do actually reverse the inequality. And that tells us that 1 over n times the square root of n to the 4th plus 1 is less than 1 over n times the square root of n to the 4th. And again, doing some algebra, n times the square root of n to the 4th is just n cubed. So this completes our justification of what we had to show in order to use the direct comparison test. And so the direct comparison test formalizes for us this idea that the series we were given and the series we introduced have the same behavior. And we could conclude by the direct comparison test that our given series converges. Now let's suppose we wanted to finish the problem using the limit comparison test. What we need to do, as we saw before, is look at this pretty nasty limit, which is a fraction of fractions. So the first thing I'll do is simplify that a bit by multiplying by the reciprocal of 1 over n cubed, so that I am computing the limit as n goes to infinity. The limit as n goes to infinity of n cubed over n times the square root of n to the 4th plus 1. Then again, I'll use these ideas of n behavior to get rid of the nasty terms. That little plus 1 that's underneath the square root sign is unimportant, so I'm going to throw that away, and I'll compute the much simpler limit. Limit as n goes to infinity of n cubed over n times the square root of n to the 4th, which is the limit of as n goes to infinity of n cubed over n cubed, which is 1. Now, what we need to check, so we've seen that the limit exists, what we next need to check is that the limit is in the right range, which is that it's some number. Any old number in the world would be fine, as long as it's not infinity, which is a concept, and it's not 0. So 1 certainly satisfies these properties, and this completes our justification using the limit comparison test. So we could also use the limit comparison test to determine that this series we were given converges. Now let's do one more example here with just 1 or 2 little extras in it. So let's try to determine the convergence or divergence of the series sum n goes from 2 to infinity, 1 over the quantity 2 to the n minus 1. And our first step is always to take a look at the function, the terms that we're adding up, and use the ideas of rate of growth to concentrate on what's important. So again, this minus 1 is not really helping us very much. In terms of rate of growth, it's unimportant, and we could throw it away. And so the series that we think we should compare to is the series sum as n goes from 2 to infinity, 1 over 2 to the nth power. Now, the reason that this series is kind of nice is we can use a little trick and rewrite 1 as 1 to the n, and then we can factor that n out here. And we can think of this series as the sum as n goes from 2 to infinity of 1/2 raised to the nth power, which is something we've seen many times before. This is a geometric series, and that's great because we are very comfortable with geometric series. In particular, this is a geometric series where our ratio is 1/2, and that means that we've got a convergent series with 1 over 2 to the n. The sum of that as n goes from 2 to infinity by the geometric series test. One thing that makes this problem worth doing is that this is an example of a problem where we actually can't use the direct comparison test. Since we're trying to compare the series we were given with the series sums n goes from 2 to infinity of 1 over 2 to the n, and we know that that is a convergent series, what we would need to show in order to use the direct comparison test is that what we were given, the nasty terms, we would have to show that those terms are always less than the terms in this nice series that we've introduced, which have the form 1 over 2 to the n. However, we see by evaluating this and plugging in some values for n that this is untrue. 1 over 2 to the n minus 1 is actually greater than 1 over 2 to the n. And so we can't use the direct comparison test. The terms that we're looking at are actually larger than what we're trying to compare to, and the direct comparison test is inconclusive in this case. We can, however, use the limit comparison test and take the limit as n goes to infinity of the terms we're given, the messier terms, divided by the terms we ourselves introduce, the 1 over 2 to the n terms. Again, we multiply by the reciprocal so that we're looking at the limit as n goes to infinity of 2 to the n all over 2 to the n minus 1. And either by dividing through by 2 to the n or just by getting rid of that minus 1 in the denominator for rate of growth, we see that this limit as n goes to infinity is 1. And again, 1 is a perfectly good number. It's between 0 and infinity. And we can therefore apply the limit comparison test to conclude that the series we were given here is also convergent.